So now, ladies and gentlemen, we are going to have a final presentation of day one. We are very happy to have Dr. Rajeev Rastogi back with us today. Quickly, for all those who just joined in, let me tell you a little bit about who Dr. Rajeev Rastogi is. He is currently the lab director of Machine Learning Lab at Amazon India, where he is developing ML platforms and applications for the e-commerce domain. Previously, he was the vice president of Yahoo Labs, Bangalore, and the founding director of the Bell Labs Research Center in Bangalore, India. Rajeev is an ACM fellow and a Bell Labs fellow. He's extremely active in the field of databases, data mining, and networking, and he has served on the program committees of several conferences in this area. He currently serves on the editorial board of CACM and has been an associate editor for IEEE Transactions on Knowledge and Data Engineering in the past. He's published over 125 papers and holds over 50 patents. He has received his BTech degree from IIT Bombay and a PhD degree in computer science from the University of Texas and Austin. And here he will be joining us to take us through a session on machine learning modeling best practices. Over to you, Dr. Rajeev.
Thank you. Thank you for the introduction. I'm having some network issues, so I'm going to request the organizers to run the slide deck. Can you hear me?
Yes.
Yes, Dr. Rajeev.
Okay, great. So what I'm going to do today is talk about machine learning modeling best practices that we've learned over the past few years as a result of launching machine learning solutions in production here at Amazon. Next slide, please. Now, in this talk, I will cover 10 modeling best practices that are shown here. Moving to the next slide. So the first best practice is to optimize directly for economic value as opposed to ML metrics such as precision and recall. And here I want to talk about an example from packaging. Now, we have seen customers complaining about damaged products and excessive product packaging. This is not only wasteful and bad for the environment, but it also increases our packaging and concessions costs. Now, this slide here shows the different types of packaging arranged in increasing order of costs. The packaging types on the right, such as corrugated boxes, are more expensive, but they also lead to fewer damages and lower concessions. So as you can see, there's a trade-off here between packaging costs and concessions. Next slide, please. Now, earlier we followed a rule-based approach to select the packaging type for a product, primarily based on its category. Recently, we've switched to a economic value-based approach. So let me explain what that means. So, we have developed an ML model that can predict damage probability for a product given its packaging type. Now, these damage probabilities are then used to select the optimal package type for each product that minimizes the total cost of packaging and concessions paid for damaged shipments. So this term here, that is the product of damage probability and concessions amount, is the expected concessions cost due to damage. So our ML-based approach reduces concessions costs by selecting a robust packaging type like corrugated box for products that are more susceptible to damage. Conversely, for products that are less prone to damage, it selects an inexpensive packaging type like poly bag, and this helps to reduce packaging material costs. Now, since we use cost estimates to select the package type for each product, we need to ensure that these damage probability estimates are well calibrated. And good techniques to ensure that probabilities output by models are calibrated are things like isotonic regression, Platt scaling, and so on. Moving to the next slide. At Amazon, we focus on the long term. So our ML solutions should also optimize for long-term value. Now, actions have a long-term impact or a downstream impact. A product purchase can lead to more purchases, thus resulting in an increase in profit. On the other hand, a damaged product may cause the customer to shop less on Amazon or even stop shopping on Amazon altogether. And this can lead to a reduction in profit. Now, to estimate the downstream impact of an action such as a product purchase or a damaged product, we create two sets with similar data distributions. One set is a treatment set containing customers who have performed the action. The second set is a control set with matching customers who have not performed the action. Here, matching between the treatment and control sets is carried out using customer features such as demographics, for example, age, gender, location, could be the tenure, purchase history of the customer, and so on. Can you click? So the difference in 1 year profit between treatment and control gives us the downstream impact of the action. Now, this is a very important area. In fact, the latest Nobel Prize for Economics went to the inventors of these techniques to compute um, downstream impact using causal inference techniques. Next slide. Now, in the packaging equation that I shown earlier, concession costs captures the short-term costs due to product damage. So we add to it DSI damage to capture the downstream impact of damage on customer purchases. Essentially, DSI damage is the long-term reduction in profit due to damage. Next slide. The third best practice that I want to talk about is around generating uncertainty estimates for predictions. Now, product weight data is a critical input within Amazon to, calculate fulfillment fees for sellers, to determine the package recommendation for a product, and so on. So there are many applications of it. However, these weight measurements are often erroneous due to errors in in-house measurements, as well as sellers entering inaccurate information while listing products. So the business objective here is to predict product weights with error less than X%. Here, X is some number. I've just not revealed it for whatever confidentiality reasons. So the approach that we use here is to train a light GBM model with quantile loss to predict the different percentile weight values. Now we can use this model to predict weights for all the products, and this would give us a coverage of 100%, but it would also result in a high MAPE of X plus 12%, which is higher than what was required by business. So this doesn't really meet the business requirements that we have. Now, an alternate strategy here is to predict weights only for products that for whom the difference between the 95th percentile and the 5th percentile value is bounded above by 3.3 times the 50th percentile weight value. Now, once we do this and restrict the products for which we predict weights, the MAPE reduces by 1500 bips from X plus 12% to X minus 3%. And this clearly meets our business requirements of a MAPE of X%. Of course, this reduction in MAPE is accompanied with a loss of coverage. We predict weights for only 83% of products as opposed to 100% of products. So what we see here is by suppressing predictions for products whose predictions have a high variance, we are able to reduce MAPE below X% and meet the business requirements. So in general, it's a good practice to generate probability distributions as opposed to point estimates. There are several techniques out there to generate probability distributions. One can use quantile loss. For deep neural networks, it's possible to generate probability distributions using dropout. You can generate different samples from the posterior of the network, and dropout essentially zeroes out the output of each neuron with a certain probability. Now, unfortunately, computing exact posteriors is intractable for all but the simplest of models. For example, for Bayesian linear regression, we can compute the exact posterior in closed form. So moving to the next slide. Now, in the packaging scenario, we may not have accurate estimates of damage probability. This could be due to insufficient training data, there could be data distribution changes, or you could have new products and package types. So, that's a typical cold start scenarios. Now, most ML models out there will return point estimates for P damage, and that corresponds to the mean. However, again, in reality, there is a probability distribution over damage probability as shown in this slide here. And the point estimate corresponds to P mean. In fact, the probability distribution over damage probability may have a high variance. And this becomes a problem if you're using the point estimate P mean to select the package type for a product. So for example, if the true damage probability is less than P mean, then P mean will end up overestimating damage probability and use excessive packaging. On the other hand, if the true damage probability is greater than P mean, then P mean will end up underestimating the damage probability and use too little packaging. So the question here is, how do we select the package type for a product when we have a probability distribution over damage probability? And the approach we use is based on Thompson sampling, which is an explore-exploit technique. Thompson sampling draws a sample from the posterior distribution over damage probability for each packaging type, and then it selects the packaging type that minimizes packaging and concessions costs. So essentially, what Thompson sampling is doing is it's selecting a package type that either has low damage probability, which corresponds to exploitation, or a packaging type whose damage probability has a high variance, so which corresponds to exploration, right? And what exploration is doing here is it's generating training examples that help to reduce variance of the damage probability for the package type. Next slide. The fifth best practice that I want to talk about is generating explanations. Now, fulfilling an order involves multiple entities such as customer, seller, delivery associate, and so on. As a result, any of these entities may be responsible when a package goes missing. So for example, if a customer complains that he or she has received a bar of soap instead of a smartphone, then it is possible that the delivery associate switched the product, or the seller could have shipped the bar of soap instead of the smartphone, or the customer could be lying and falsely claiming that he or she received the bar of soap instead of the phone. So, the problem here is thus to identify or pinpoint the entity responsible for the missing item. Next slide. So we use attention weights in neural networks to pinpoint the entity responsible for the missing item. As shown in the slide, seller, customer, and DA features are input into the neural network. Attention weights alpha I are computed for each entity by applying a transformation function f to the hidden state for the entity, as shown in the equation here. And then the final probability of the item going missing, which is y, is for the order is then obtained by applying the sigmoid function to the sum of the hidden states weighted by the attention weights. Now, the attention weight for each entity here captures the likelihood that the entity is responsible for the missing item. Okay, so essentially it's giving you an explanation of the prediction. And entities who are responsible for the missing item will end up with high attention weights, while entities who are not responsible for the missing item will end up with low attention weights. And once we have pinpointed the entity responsible for the missing item, we can trigger the appropriate action, such as investigating the entity. Next slide. Can you please do a click? Yeah, yeah. Now, for the problem of identifying the entity responsible for the missing item, AUC of our attention weights model is 13% higher compared to a sugar index based approach. Here, the sugar index for an entity is the fraction of orders involving the entity that result in a missing item. Okay. Moving to the next slide. Now, the Amazon product catalog in India has over 200 million products. However, since sellers are responsible for populating product metadata on our marketplace, some of these product listings end up having defects. And these poor quality listings erode customer trust, they hurt conversions and sales, and they also lead to excessive returns. So this slide here shows defects involving mismatches between product attributes such as titles and images. So here in the first uh, uh, screenshot, you can see that the title says that the product is a t-shirt, but the product image shows a bag. In the second screenshot, you can see that the title says that the color of the product is blue, but the product image shows a pink dress. So if you were a customer, you wouldn't know whether if you, whether you would receive a blue or a pink dress if you place an order. So most likely you wouldn't purchase this product. Next slide. And in some cases, attribute values may be missing. Uh, uh, for example, color may be missing for certain products in the catalog, and this can hurt search refinement experience. So this orange dress shown here gets dropped from search results when the customer applies the orange yellow color filter because the attribute value orange is missing in the catalog. Next slide. So key capability now to identify and correct these defects that I just showed in the past two slides is the ability to extract attributes such as color, material, pattern from product titles and images. So as shown here, we can infer the title from the product title, the color from the product title and image. We can infer the material from the product title, and we can infer the pattern from the product image. And we use ML models to extract attribute values from product titles and images, and then use these extracted values to backfill missing attribute values in the product catalog. Next slide. Now, a simple approach, a supervised learning approach here is to train deep learning models to predict attribute values, right? And training data for these models is manually generated using the color attribute as an example. Human annotators would label thousands of images as red, blue, and so on. And using these label data, we train an image classifier that predicts the color for a given product image. Shown in the slide, we use exception as a model architecture for the image classifier. It maps the product image to a compact embedding, which is then used for classification, right? Next slide. Now, the supervised learning model has a 64.1% recall at 90% precision. Now, this is this is pretty good, but it requires manual labeling. So moving to the next slide. And manual labeling to create this training data is expensive. And if we want to scale to hundreds of attributes, we need a way to eliminate human-generated training labels. So the sixth best practice is really around reducing manual effort to generate training labels. Next slide. And here we use CLIP. Uh, CLIP stands for Contrastive Language Image Pre-Training, and this was proposed earlier this year to learn image representations from text and perform zero-shot predictions without manually labeled training examples. So let's see how CLIP works. CLIP jointly trains an image encoder and a text encoder to predict correct pairings of a batch of image text training examples. Now, to do this, CLIP learns a multimodal embedding space by jointly training the image encoder and the text encoder to maximize the cosine similarity of image and text embeddings of real pairs in the batch while minimizing the cosine similarity of embeddings of incorrect pairings. So essentially, embeddings of paired text and images are brought close together by uh, maximizing their cosine similarity, while embeddings of unpaired text and images are pushed away from each other by minimizing the cosine similarity. Next slide. Now, CLIP is pre-trained on to predict if an image and a text snippet are paired together in its data set. Uh, Now, to do zero-shot classification, we can reuse this capability. Essentially, for an image, we look at all the attribute. We look at the attributes, and we use the names of all the attribute values, such as blue, green, black, and so on, as shown here, as the set of potential text pairings, and predict the most probable image text pair according to CLIP. So in more detail, we first compute feature embeddings of the image encoder of the product image and the feature embedding of the set of possible texts by their respective encoders. And we then predict the attribute value with the maximum cosine similarity of the embeddings. Okay. Now, next slide. CLIP has a 47.3% recall at 90% precision. And if you look at the number here, this is much worse than the supervised learning model. And this is because CLIP is pre-trained on 400 million image text pairs collected from a variety of publicly available sources on the internet. Essentially, Amazon data is not used here during pre-training, right? So moving to the next slide, we will look to fix that. Now, since CLIP is used to predict attribute model values for product images, we additionally pre-train CLIP on product image title pairs from the Amazon catalog. Next slide. So pre-trained CLIP has you can see that there is a bump in recall here at 90% precision. It goes up from 47.3% to 53.4% as a result of pre-training. Although its performance of pre-trained CLIP is still worse than supervised learning, and this is because the training process maps the entire title and image to the same space without leveraging attribute-specific training labels. Next slide. Now, a large number of products have attribute values populated in the catalog by the sellers. So as you can see on the right-hand side of the slide, we have our product catalog where a seller has entered the attribute value black for color, right? So similarly, other attributes also may have been entered. The values may have been entered by sellers. So we can leverage these attribute values to generate training labels, right? And and then use these training labels. Next slide. And then use these training labels to fine tune the clip image encoder to predict these attribute values. Next slide. Yeah, next slide. Now, uh, yeah, even though these catalog labels are not particularly uh, accurate compared to manual annotations, what we found was fine-tuning clip using these catalog labels. We were able to increase the recall at 90% precision from 53.4% to 63.4%. So we got a 1,000 bips improvement in recall as a result of leveraging the attribute values in the catalog. The seventh best learning, as you can see here, is to leverage as many signals as possible. Now, besides product image, the product title also has a lot of valuable information about attributes. Uh, next slide. Next slide. Yeah, as you can see that here from the product title, Janasaya women's black cotton western dress, we can conclude that the color of the dress is black and the material of the dress is cotton, right? So instead of only fine tuning the image encoder, we